So it's great to see all of you back in class this week. I didn't scare you off from the first week of class. Today, we are going to look at basic laws of limits and looking at how to solve them algebraically using these laws, and then giving you tricks of how to manipulate certain limits when they don't fall out and give us the information that we need. So I'm going to share my page with you. There are some pages and notes that I had hooked up to the module 2, week 2, that I will use somewhat in this week's lecture. So you can print them out if you wanted to and follow along. The other thing I just wanted to mention really quickly is that week 2 module is open up now. Sorry, that was an error on my part. I forgot to push the little green publish button, and you should be able to get in and watch those videos on Monday. But those videos on Monday are pretty much a review of what we covered Wednesday and Thursday last week, with looking at a limit graphically and being able to determine what that limit is. So let's get started with looking at the basic limit laws. So let me pull again up my page and share that with you. Okay, so we have some basic limit laws that we're going to use to help us solve for limits algebraically. And so the first one says, if C is a constant, then if we look at the limit as x approaches some value, we'll call it A in this case, of a constant, this is equal to C. And so let's just think about this and what this is saying to us graphically. And so if we had some equation that we had y is equal to C, where f of x equals c, where c is equal to a constant. Remember when we had y equals a constant, the graph of that looked like a horizontal line, right? And so let's just say in this case, c is above the x-axis. And we graphed it, y is equal to c. So this is just a horizontal line here. So if I'm looking at the limit as x is approaching a, of the value c, well, let's just say arbitrarily, let's say a is over here. And so if we are looking at the limit as x is approaching a, remember we're looking at what's happening as we get closer and closer to the x value equals a on the left, what's happening to that y value. And so notice as we're getting closer and closer to a, on the left, the y value that we're getting closer and closer to, which is it's just the same, is equal to c. And we kind of denoted that with the left with that little negative exponent, and this was equal to c. If we looked at the limit here as x was approaching a on the right, and so we denoted that with a plus symbol of c. So as we're coming in from A on the right-hand side, we're looking at our graph and we're looking at what is that y value we're approaching as x gets closer and closer to A on the right. And that y value that we're getting back is also C. We talked about in order for a limit to just say the limit exists, it has to, left-hand side has to equal the right-hand side. So the limit as x approaches A of a constant C is equal to C. So if you take a limit of a constant as x approaches any value, then it's just equal to that constant. So the second case also, if we think about it graphically, also makes sense. And what the second statement says is if we have some function f of x equals x, or another way to write that is y equals x, and we looked at that graph, right? We would have this diagonal line going through the origin. Think about it, plotting points, right? When x is 0, y is 0. When x is 1, y is 1. X is 2, y is 2. And that vertical line is going through the third and first quadrant. When x is -1, y is -1. So we have, right, just a line here. And so if I'm looking at the limit as x is approaching a, so let me just write a on the graph somewhere. So let's say a is out here of the value of just x. Well, let's look at what's happening on the left-hand side. The left-hand side, let's put in that negative value. So on the left-hand side, if I follow the graph, as my x's are getting closer and closer to a on the left, that y value that I'll be getting is a. And if I look at that limit as I'm approaching x on the right of x, so I'm coming in on the right of x equals a, my y value I'm getting closer and closer to is also a. And so that tells me that this limit exists. And the limit as x approaches a of x equals a. Okay. So those are two basic limit laws. I'm going to give you some more laws, limit laws. And in conjunction with these two, they're going to make our life pretty simple when we're looking for finding limits. Okay, so we're going to look at some more limit laws, and normally we're not going to sit here and use these laws and show them each time, but I want to go through the laws, and then I want to go through a couple of examples using the laws, and then we're going to jump into just direct substitutions when we take limits, and you'll understand what I mean in a moment after we go through some of these examples. But looking at our theorem here, it says let capital L and capital M, little c and k, let them be real numbers. And we're assuming here that if we looked at the limit as x is approaching c of f of x, we're going to get a y value back of capital L. And if we looked at a limit as x is approaching c of a different function g of x, and we got back capital M, then we can say the following occur. Okay, so first one, pretty straightforward. The sum rule. And the sum rule says, if we're going to look at the limit as x approaches c of f of x plus g of x. So basically, we have more than one term in there when we're looking at the limit as x approaches c of some function. Basically, if we split up each term and treat it as a different function, we can look at the limit of the first. And maybe I should write this down. So we can look at the limit as x approaches c of f of x and break it down as plus the limit as x approaches c of g of x. And we saw up here, the limit as x approaches c of f of x was our L value, and the limit as f of x approaches c, x approaches c of g of x was equal to m. So technically, same idea. If you had a subtraction in between your two terms, we can treat the terms as different functions if we want. And I'm just going to go up here. It's the same thing up here. I could put a minus in here. So if I'm looking at the limit here as x approaches c of something, parentheses, f of x minus g of x in the parentheses, I'm just going to take what the limit of the first is, which was L, minus the limit of the second function, in this case, which was M. The next one helps us if we have some number in front of our variable. This is the constant multiple, and it says here that if you look at the limit where you have some constant in front of your function f of x, we can pull the constant in front or the coefficient in front of our limit. So let me just write out what that says. So this right here, we can say this is the same thing as pulling our coefficient out front and then taking the limit as x approaches c of f of x. And if we did that, we would have that coefficient in front, which is k, times the limit as x approaches c of f of x, which we saw was capital L. So same idea with products. If you're looking at the limit of x approaches c of f of x times g of x, basically what we're doing is we're looking at the limit of the first function. So a limit as x approaches c of our f of x function, all times the limit as x approaches c of our second function, g of x. Well, we saw the first one was equal to L when we took the limit, and the second one was equal to M when we took the limit. Okay, so that it follows down similarly for each of the other ones. So quotient rule, if you have a quotient and you're looking at the limit of a function f of x divided by g of x, we can look at it as the limit of the numerator all over the limit of the denominator. And in this case, limit as x approaches c of f of x was L, and the limit as x approaches c of g of x was M. Got to put that one stipulation in there that we cannot have our denominator equal to 0. So that limit as the denominator, x approaches c of g of x, that limit can't be 0. The power rule is just saying if you're raising something like x squared, that's a power, right? We're squaring x, or the cubed root of x. Actually, that would be the root rule below. But remember, we could rewrite roots as power, so that's why I'm just saying that. But so that's just saying that we can look at the limit of the function in here, f of x, and then raise that the answer to our limit to that power. So really here, I'm saying this is the same thing as looking at the limit as x approaches c of f of x, and then raising it to that power, that nth power. And similarly, the root rule, again, because roots can be written as radicals. So if we have a limit of a radical, we could rewrite it where we are looking at the radical, so the nth root, and then what's underneath the radical, the radicand, we can look at the limit of what was underneath the radical. So limit as x approaches c of the function underneath the radical f of x. You got to be a little bit careful because if we're talking about real numbers, if n is even, so if we're taking a square root or a fourth root or a sixth root, if that number is even, in order for our value to be a real number, we have to have what's underneath that radical to be positive. So that's why it says if n is even, we assume that f of x is greater than or equals to 0 for x in the interval containing c. Because if not, then we would have had an imaginary number. Okay. Okay, so we're looking at the following example where we're looking at the limit as x is approaching -3 of the quantity x squared minus 13. In that quantity, we have a quantity cubed. And so let's look at this limit and let's use the limit rules that we just talked about to justify each step that we're doing to find out what the limit of this is. And so first thing I see is that we have this power here. And so I want to use the power rule. So by the power rule, we could rewrite this as putting the limit inside. So we can look at the limit as x is approaching -3 of x squared minus 13. And this is quantity cubed. So now I'm looking at inside that bracket when I'm looking at the limit of now. And notice that I have x squared minus 13. So I technically have two separate terms in here. And I can think of one function being x squared and another function being 13 or -13. And so I can use this difference rule. Let's use this difference rules now. So using the difference rule, we can break up this limit inside this bracket. And so doing that, I'm going to have, I still have this cubed root, but I have the limit as x is approaching -3 of x squared minus the limit as x approaches -3 of 13. And then that is quantity cubed. So I'm almost there. Notice that the limit as x approaches -3 of x squared, that's a power rule again. So we're going to use the power rule again. So I still have this cube, this bracket cubed, but now inside there, we have this limit as x approaches -3 of x, and then I'm squaring it by that power rule minus that limit as x approaches -3 of 13, and then I still have to cube it. So those first basic limit laws that we looked at, right? Those are using those two right there. So the limit as x approaches, some value a of x was equal to a. And so in here, this was number 2 from our limit law above. We have, let me just rewrite the bracket because we haven't done it yet. But this limit here, this is -3. But then I still have this square here. Minus, now I'm looking at the limit law of a constant. So limit as x approaches, and that should be -3 of 13. So limit of a constant, no matter where we're going, is equal to that constant. So the limit as x approaches -3 of 13 is just equal to 13. And then quantity cubed. I don't think that was called anything in particular. So by the basic limit laws. And now let's just use order of operations to simplify this down. And so inside the main parentheses or brackets in this case, first, exponents come first, -3 quantity squared is +9 minus 13 bracket quantity cubed. 9 minus 13, that is -4. And if I cube -4, well, 4 times 4 is 16, 16 times 4 is 64, but I'm multiplying negative and odd number times, so it's going to be -64. Okay, so I justified this by using all of those limit laws that we just talked about. Normally I won't ask you to do that, but you need to know that what we're doing and why we're doing it works. And so really, when we're doing these limits, just do direct substitution. That's the first thing you want to try. So look at it at this limit. Let's go through the same problem. As x approaches -3 of x squared minus 13 cubed. And let's look at this by just using direct substitution, and wherever we see an x, we're going to replace it with this -3. So if I did that, wherever I see an x, I'm replacing it with -3. So I have a -3 quantity squared minus 13, and then I'm cubing that. So if I look at my order of operations here, I get -3 quantity squared is 9, 9 minus 13, and then I cube this. Well, that's -4 cubed, which is equal to -64. So that's a lot faster than going through and justifying each step and using those laws. But why we can do this direct substitution like we're doing is because of that limit law, or those limit laws. So I'm going to pause for a second while you guys finish writing. Okay, so the question was, is it just as easy, as just plugging in that whatever x is approaching into wherever we see the variable? And yes, normally it's just that easy. That's the first thing you want to try, is just plug it in. That value is whatever x is approaching into wherever you see x in that function. And one of the rules that justifies this too, and it's using those limit rules, is this limits of polynomials. So because of the limit laws, we can use this limit of polynomials, which basically says if we're working with a polynomial, so remember what it meant to be a polynomial that had this definition, mathematical definition, and it looks kind of scary, but it's not that bad. Basically, it's just saying that p of x is equal to a sub n x to the n plus a sub n x to the n minus 1 plus ... plus a sub 0. N has to be a whole number for it to be a polynomial. So remember, we couldn't have radicals as our exponents, fractions as an exponent. If we did, that wasn't a polynomial. The other thing that we had to do was, and the other thing was if our variable was a negative number. Sorry, the exponent was a negative number, that would bring it down to the denominator. The other thing that's going to help us is that maybe you have a rational function where what you have in the numerator is a polynomial all over what you have in the denominator is a polynomial. If that's the case, and you're looking at the limit as x approaches c of this rational function, you can just plug in, again, what x is approaching wherever you see the variable in the numerator and denominator to get our answer. Okay, so now we're going to jump in and do examples by just plugging in values wherever we see our variable. Okay, so we're looking at here the limit as x is approaching -2, x minus 2 in the numerator, all over x squared plus 5x plus 6 in the denominator. And so by these limit laws, notice that our numerator, or these theorems, look at our numerator x minus 2, that is a polynomial. Our denominator x squared plus 5x plus 6, that's also a polynomial. So basically I can look at direct substitution in the numerator and in the denominator wherever I see the variable x. And so that's the first thing that you want to do and start. And so if we do that, I usually put in parentheses wherever I see my variable. So I have parentheses minus 2. I have a parentheses squared plus 5. I see an x, so parentheses and then plus 6. And then I go in and wherever I see the parentheses, I replace it with what x is approaching, in this case, -2. So let's simplify order of operations. Numerators like a parentheses, denominators like a parentheses. In the numerator, I get -2 minus 2, which is -4, all over -2 quantity squared is 4. 5 times -2, that's -10, plus 6. So notice I get -4 over 0. So we have a problem here because of this right here is undefined. Can't divide by 0. If we looked at our function, so kind of thinking back to college algebra, if we looked at our function, let's say f of x equals this, x minus 2 all over our denominator, x squared plus 5x plus 6. And we were to graph this, we graphed rational functions, we looked at asymptotes. Do we have any horizontal or vertical asymptotes in here? And notice that we have a vertical asymptote. So recall vertical asymptotes those occur on values which set the denominator equal to 0, but not also the numerator. So that values, vertical asymptotes occur at values which set the denominator equal to 0, but not also the numerator. So if we go back to this function, f of x, and we factored that denominator, we'll notice that we have a vertical asymptote at x equals -2. Oops. Okay, so if we look at the denominator, x minus 2, and we factor, if we factor the denominator, x squared plus 5x plus 6. So what multiplies to give us 6, but adds to give us 5. So 2 and 3. So I see that that factors as x plus 2, x plus 3. And so values which set this denominator equals 0. So when x plus 2 equals 0, that's when x is -2. And when x plus 3 equals 0, that's at x equals -3. So we have vertical asymptotes at x equals -2 and x equals -3. So I just I want to review a little bit on how to graph these, because it's really important in calculus, especially calculus 2, is to be able to graph your functions. And so here, let's look at our graph. We know that we have vertical asymptotes at -2 and -3. So remember, we denoted asymptotes by that dotted line on the graph. It's undefined there. And we're looking at the limit as x is approaching -2. So we're looking at what's happening to the graph as we get closer and closer to that -2 value. Well, remember that as vertical asymptotes, the graph is either shooting upwards or downwards as we approach that x value. Okay. Let's look at that. So if I look at the limit as x is approaching -2 on the left-hand side, of this x minus 2 all over. I'm going to keep it in factored form just so we can talk about positive and negative numbers without actually calculating things. So x plus 2, x plus 3. So if I'm looking at x coming in to negative 2 on the left-hand side, I'm going to just make this bigger. That means I'm plugging in like negative 2.1, negative 2.001, negative 2.0001. It's getting closer and closer on this left-hand side. So let's just talk about the numerator. If we plugged in an x value that was close to negative 2 on the left, so again, negative 2.1, negative 2.1 minus 2, that would give my numerator to be a negative number. Divide by, well, if I plug in negative 2.1 or something to the left of negative 2 into this x plus 2, notice that that's also going to be negative. If I plug in a number to this factor x plus 3, well, negative 2.1 or something close to negative 2 on the left and adding it to 3, that's going to be a positive number. So as we're looking at this, we have this negative number on the top divided by a negative. So we know our result is positive. So I know as x is approaching negative 2 on the left, it's shooting upwards. I can kind of do the same sort of idea. So this is going to, let me just write this down. So this right here, this is going to positive infinity. So if your limit doesn't go to one particular number, the limit doesn't exist. But limits are actually talking about what's happening to the graph. And so sometimes, even though it doesn't exist, we want to know why or what's happening there. And so it's shooting upwards, it's going to positive infinity. If we wanted to look at that limit as x is approaching negative 2 on the right-hand side, we can kind of do the same sort of reasoning by seeing is that going to be a positive or a negative number when we're plugging in x values coming in on the right-hand side. So as I'm coming in on the right-hand side, I'm plugging in numbers close to negative 2 on the right, so like negative 1.9. That's close to 2 on the right, negative 1.99. So let's talk about in the numerator. Well, negative 1.9 minus 2, or anything close to negative 2 on the right, that's always going to be negative. But if I plug in negative 1.9 and add 2 to it, that's going to be positive for that first factor in the denominator. And a negative 1.9 or negative 1.99 plus this 3, that's also positive. So I notice that my value that I'm going to get back is going to be a negative number. So this has to be shooting down to negative infinity. So as x is going to negative infinity, I'm sorry, negative 2 on the right, this shoots downwards. Okay, so we kind of showed why our limit doesn't exist by doing some mathematical reasoning as we come in on the left and the right and showing that it's not any particular value and showing that this was vertical asymptote there. We could have done this by using the calculator and just showing as we plugged in numbers on the left and the right of negative 2 as we got really, really close. You would notice that your y value on the left-hand side was being positive and not going to one particular number, going to positive infinity. And if you chose numbers on the right-hand side, they would have been negative and blowing, the absolute value blowing up. Okay. So that is one case where it's undefined. But let's say that this was a little differently. And let's look at the problem, almost identical problem, but instead let's change that numerator to +2. So let's say this was a limit as x approaches -2 of the numerator x plus 2 all over the denominator of x squared plus 5x plus 6. So let's see what happens in this case right here. And so if we did direct substitution like we had done before, well, we would still get 0 down in the denominator. But this time when we plug in -2, wherever we see an x in the numerator, we get -2 plus 2, which is also 0. This is, and we kind of discussed this last week, and I said we get back to it, but this is what is called an indeterminate form. This doesn't tell us anything about the limit as x approaches -2 of this function. We have to manipulate this. So we're manipulating what you're taking the limit of. So if you're getting 0 over 0, that's telling me that basically my denominator and numerator have a factor in common. And again, if we factor our denominator, so I have x plus 2 in my numerator, and factoring x squared plus 5x plus 6, remember that was x plus 2 all times x plus 3. Even though this is undefined, actually, I should be careful. Y equals x plus 2 all over x plus 2 all times x plus 3 is undefined at x equals -2 and x equals -3. But we can look at the simpler form. As long as we put on the stipulation, it's undefined there. We can say, well, this is the same thing as the limit as x is approaching -2. Well, the factors of x plus 2 cancel, so I'm only left with 1 in the numerator, and I'm left with x plus 3 in the denominator. So now let's do direct substitution. Wherever we see an x, we're going to replace it with -2. And so doing that, I get 1 all over -2 plus 3, which is 1 over 1, which is 1. So it's undefined, and we talked about limits can exist if it's undefined at a value. And what's happening as we get closer and closer to this open circle at x equals -2, our y value is getting closer and closer to 1. So we'll look at more examples of this on Thursday, where we're going to continue to look at this algebraic approach of limits where we can just substitute in the value, but I'll give you some more examples where we get this indeterminate form 0 over 0. We would have to manipulate it a little more. Let me stop there. The video that's for tomorrow's lecture, I'll have those posted for tomorrow, because class just for tomorrow will be not held through Zoom, and you'll get your videos off of week 2 module, which is now open, and they'll be posted there by this evening sometime. So watch those. I just might do just a couple short videos for you to watch. The ones on Monday, again, you can look at that if you want to get and see more of the concept of looking at graphs and looking at limits by looking at the graph. Otherwise, you should be able to do all the homework still that we've had with those videos.